In this video, we're going to talk about sound waves. A sound wave is a type of longitudinal wave. Now you need to know the difference between a transverse wave and a longitudinal wave. A wave on a string, for example, forms a longitudinal wave. The wave is moving in the x direction, but the oscillations are up and down. It's perpendicular to the wave motion. The oscillations are in the y direction. Whenever the oscillations are perpendicular to the wave motion, you have a transverse wave. A sound wave is not a transverse wave. A sound wave is a longitudinal wave. A sound wave is basically a pressure wave. In air, as sound travels through air, you can have regions of high and low pressure. The regions in dark gray represent the regions of high pressure, where the molecules are close together. The regions shaded in white are areas of low pressure, where the molecules are spread apart. So a sound wave in air is basically an oscillating pressure wave. Now the reason why a sound wave is considered a longitudinal wave is because the oscillations are parallel to the wave direction. Notice that the oscillations are in the x direction. So in the region of low pressure, you have expansion. The air molecules expand in this region. This is also known as rarefaction. In the regions of high pressure, you have the molecules compressed. Compression occurs at that region, so the density is higher at that point. So for sound to travel, it needs a medium. Sound can travel through any fluid like a gas or a liquid. It can travel through water, or it can even travel through solids. But sound doesn't travel through space. Because space is empty, there's no molecules to carry the sound wave, because sound is basically a pressure wave. The speed of sound in air is about 343 meters per second. This is at a temperature of 20 degrees Celsius. The speed of sound depends on things like temperature, density, and even the type of material that sound travels through. For solids, the speed of sound is equal to the square root of the elastic modulus divided by the density. If you increase the elastic modulus, the speed of sound will increase. If you increase the density, the speed of sound will decrease. This equation applies for solids. For liquids and gases or any type of fluid, you can use the bulk modulus. If you increase that, the speed of sound increases. These equations, they look similar to the equation that gives you the velocity of a standing wave, or the velocity of any wave on a string. It's equal to the tension force divided by the linear density. So as you can see, the speed of sound is inversely related to density. As the density increases, the speed of sound decreases. A good example to illustrate this is comparing the speed of sound between air and helium. Helium is lighter than air. You notice because if you put helium inside a balloon, the balloon will rise. The speed of sound in air is about 343 meters per second. The speed of sound in helium is about 1,000 meters per second. Now the elastic factor, or the elastic modulus, is roughly the same for these two gases, but the speed is higher in helium because helium is less dense than air. So as we can see, whenever you increase the density, the speed decreases, and if you decrease the density, the speed will increase. Interestingly, the speed of sound in solids tends to be much higher than that of liquids, and the speed of sound in liquids tends to be higher than that of gases. So if we take steel, which is a solid, the speed of sound is about 5,000 meters per second. This is a rough estimate. And in a liquid such as water, the speed of sound is about 1440 meters per second. And in air is 343 meters per second. Now we said that as the density increases, the speed should decrease. Steel is much more dense than water or air, so we should expect a lower velocity. But you need to take into account the elastic modulus, which this is much higher for solids. So this elastic factor causes the speed to increase, so apparently it must be greater for solids than liquids. But generally speaking, the speed of sound in a solid tends to be much higher than that of a liquid, and the speed of sound in a liquid is usually higher than that compared to air. The speed of sound in air also depends on temperature. If you increase the temperature, the speed will increase as well. The equation that shows this relationship is V is equal to 331 plus 0.6 times T. So at 0 degrees Celsius, the velocity of sound is about 331 meters per second. But at 20 degrees Celsius, the speed of sound is 343 meters per second. At higher temperatures, air molecules are moving faster, and so they can conduct sound at a much higher rate. So sound travels faster whenever the temperature of the air is higher. Now let's talk about some terms that you need to know. What is the definition of the word subsonic? And what about supersonic? The prefix sub carries the idea of something that's less than or below. Super means something that's greater than or above. Subsonic is less than the speed of sound. So let's say a train moving at 60 miles per hour, or let's say 30 meters per second, is traveling at subsonic speeds. A jet that is moving at 800 meters per second is traveling at a supersonic speed. Supersonic represents an object that is moving at a speed greater than the speed of sound in air. So a jet moving at 800 meters per second can create a very loud sonic boom because it's going faster than the speed of sound. Now you also need to know the audible range, the range of frequencies that we can hear sound. We can hear sound from the range of 20 hertz to 20,000 hertz or 20 kilohertz. Kilo represents 1,000. So 20 kilohertz is 20,000 hertz. As we age, the upper limit of frequency that we can hear sound decreases. So older people may not hear frequencies as high as 20 kilohertz. Some older folks may hear sounds up to like 15 kilohertz. It really depends on the individual. Dogs, for example, they can hear frequencies up to 50,000 hertz, which is 50 kilohertz. Bats can go even higher, up to 100 kilohertz. Now, what is meant by the terms infrasonic and ultrasonic? Infrasonic are sounds that have a frequency less than 20 hertz. Ultrasonic represents sounds that have a frequency greater than 20 kilohertz. A good example of infrasonic sounds are sounds that have a lot of bass. They have a very low pitch. The word pitch has to do with the frequency of sound. So like an earthquake has a very loud rumble, but it has a low pitch. Thunder, volcanoes, heavy machinery, these things, they have a low pitch or low frequencies related to them. A sound with a very high pitch has a high frequency. A good example of the use of ultrasonic waves, think of sonar. Submarines use sonar to detect moving objects that are far away from them. Even bats, they use ultrasonic waves to detect if there's an object in front of them. Now, as we mentioned before, sound is basically an oscillating pressure wave. It's a longitudinal wave. It can cause air molecules to compress or expand, creating regions of high and low pressure. So, a sound wave can cause air molecules to be displaced. So let's say if we plot the displacement of air molecules on the y-axis and time on the x-axis, we're going to get an oscillating function, basically a sinusoidal function. The amplitude of this wave is basically the height of the wave. Now this can continue. The wavelength is the distance between the two crests of the wave. The highest point is the crest, the lowest point is the trough. One cycle is basically this portion of the wave. That's one cycle. The period, which is represented by capital T, is the time it takes to complete one cycle. So the time it takes to start from this position, go up to its maximum and back to its original value, and then go down to its minimum, back to its original value, that is one cycle. The time it takes to complete a single cycle is the period. So you can find the period by taking the total time and dividing it by the total number of cycles. If you do that, you'll get the time it takes to complete a single cycle. The frequency is the reciprocal of the period. The frequency is the number of cycles that occur in a single second. So you can find it by dividing the total number of cycles by the total time. Now there's some other equations that you need to know. We know that speed is equal to distance divided by time. The distance is measured in meters. The time is measured in seconds. So the speed of the wave is basically the wavelength measured in meters divided by the period, which is measured in seconds. So we can write V as being the wavelength times 1 divided by the period. And if you recall, the frequency is 1 divided by the period. So therefore, the velocity or the speed of the wave is the wavelength times the frequency. Make sure you know this equation. Now let's work on some problems. What is the frequency of a sound wave that has a wavelength of 95 centimeters at 20 degrees Celsius? For each of these problems, feel free to pause the video and work on them yourself. That's the best way to learn physics. So the equation that relates frequency and wavelength is this equation. The speed of the wave is equal to the wavelength times the frequency. But we need the wavelength to be in meters, not centimeters, so let's convert it. 1 meter is equal to 100 centimeters. So the unit centimeters cancel. So to convert it to meters, we need to divide by 100, which is the same as moving the decimal 2 units to the left. So 95 centimeters equates to 0.95 meters. Now the velocity of sound at 20 degrees Celsius is about 343 meters per second. So now we can use the formula. So V is 343, lambda, the wavelength, is 0.95. So let's solve for F. So it's going to be 343 divided by 0.95. So the frequency is 361.1 hertz. By the way, 1 hertz is equal to 1 over seconds, or seconds to the minus 1. So if you see those units, this is the unit of frequency. By the way, for all future problems in this video, if I don't give you the speed of sound, assume it to be 343 meters per second, unless I give you a temperature that's different than 20 degrees Celsius, at which point the speed of sound may change. If I don't give you any extra details, assume that the speed of sound is 343 meters per second for the rest of the video. So let's try this problem. If a lightning strike occurred exactly 1 mile from your location, how many seconds will it take the sound waves created by the thunder to reach your ears? Now keep in mind, the speed of light is very, very high. Light travels at 3 times 10 to the 8 meters per second. So light will reach your eyes much faster than the sound waves. Sound takes a longer time to reach your ears than the light waves. So by the time you see the lightning strike, the sound hasn't really traveled that far. So how long does it take a sound wave to travel 1 mile? How many seconds? So we know d is equal to vt. We have the distance, which is 1 mile, and we have the speed, which is 343 meters per second. So we need to divide the distance by the speed. However, the units, they don't match. We need to convert miles into meters. So we're going to solve it as a conversion problem. It turns out that 1 mile is equal to 1.609 kilometers. And 1 kilometer is equal to 1,000 meters. Now, if sound travels at a speed of 343 meters per second, that means that in 1 second, it covers a distance of 343 meters. So we can cancel the unit miles, the unit kilometers will cancel, and meters will cancel, giving us the unit seconds. So let's multiply 1.609 times 1,000 divided by 343. So it's going to take sound roughly about 4.69 seconds, or if you want to, you can round it to about 5 seconds. It's going to take about 5 seconds for sound to reach your ears. So let's say if it takes 10 seconds for you to hear the thunder, that means that the lightning strike occurred approximately 2 miles from your location. If it takes 15 seconds for you to hear the thunder, then the lightning strike occurred approximately 3 miles from your location. What is the speed of sound in air at 10 degrees Celsius? So we can use the formula V is equal to 331 plus 0.6 times T. So that's going to be 331 plus 0.6 times the temperature in Celsius. 0.6 times 10 is 6. 331 plus 6 is 337. So it's going to be 337 meters per second. Now, at this temperature, what is the wavelength of a 1.5 kilohertz sound wave? So we have the frequency, but let's convert it from kilohertz to hertz. 1 kilohertz is about 1,000 hertz. So we have a frequency of 1500 hertz. So now using the equation wavelength times frequency is equal to speed, the wavelength is going to be the speed divided by the frequency. So it's 337 divided by 1500. And that's equal to 0.225 meters. So that's the wavelength, which is about 22.5 centimeters. Now the first thing we should do in this problem is draw a picture. So let's say this is the ground, and here we have a lake, and then there's a cliff, and here's the person. So the person shouts. The sound travels across the lake and is reflected by the cliff and goes back to the person. And the person hears the reflected sound wave 3.4 seconds later after the person shouts. Using this information, what is the length of the lake? Now keep in mind the time it takes to go from the person to the cliff and then back to the person is 3.4 seconds. So this is the time to make the round trip. But the time it takes to go just from the person to the cliff is half the time. It takes 1.7 seconds to go from position A to position B. So we can use the equation D is equal to VT. We're looking for the length of the lake, which is the distance that the sound travels from A to B. We know the speed of sound is 343 meters per second. And if it takes 1.7 seconds to go from A to B, then the distance that it travels is simply 343 times 1.7. So we can say that the length of the lake is 583.1 meters. So this is it. The next topic of discussion is intensity. And what exactly is intensity? Intensity is defined as the power divided by the area. Typically, the area is usually the surface area of a sphere, which is 4 pi r squared. The unit for power is the watt, and the unit for r, which is the type of distance, is meter. So intensity has the unit watts per square meter. Now keep in mind, power is work divided by time, and work is the amount of energy that's transferred. Work is measured in joules, time is measured in seconds. So 1 watt, it represents the transfer of 1 joule per second. 50 watts tells you that in 1 second 50 joules of energy is being transferred. So power is the rate of energy transfer. Now let's say if we have a sound source, and let's say 1 meter away from the sound source, the intensity is 90 watts per square meter. What will happen to the intensity if we double the distance? According to the formula, intensity is inversely related to the square of the distance. This is known as the inverse square law. So if you double the distance, if you plug in 2 for r, the intensity is going to be 1/4 of its original value. So if you divide 90 by 4, you should get an intensity of 22.5 watts per square meter. Now what if you triple the distance? What happens to the intensity of the sound wave? So 1/3 squared is 1/9. So it's going to reduce by a factor of 9. So to find it, divide this number by 9. So it's going to be 10 watts per square meter. So as you can see, if you increase the distance, the intensity decreases. Likewise, if you decrease the distance, the intensity will increase. So what is the intensity at a distance of, let's say, half a meter or 0.5 meters? What do you think the answer is? So because we reduced the distance by a half, let's plug in 1/2 into r. 1/2 squared is 1/4. 1 divided by 1/4 is 4. So it's going to increase by a factor of 4. So it's going to be 360 watts per square meter. And it makes sense because as you move closer to the source, it's going to sound louder. If you're at an event with music being played, as you walk towards the speakers, it's going to sound louder. As you move away from the speakers, the intensity will be reduced. Now going back to this equation, wavelength times frequency equals speed. At constant speed, what is the relationship between wavelength and frequency? If you increase the wavelength of a sound wave, what happens to the frequency? These two are inversely related. If you increase the wavelength, the frequency decreases. So if you increase the wavelength by a factor of 2, the frequency will be 1/2 of its original value. If you decrease the wavelength by a factor of 3, the frequency will increase by a factor of 3. So anytime you decrease the wavelength, the frequency will increase. So those two are inversely related. Now the next thing we need to talk about that is related to intensity is intensity level. The sound intensity level is known as the decibel, or is measured in units of decibel. Here's the equation. B, which is measured in decibel, which has the unit dB, it's equal to 10 times log I divided by I naught. I represents the intensity of the sound wave. I0 is the threshold of hearing. This is the lowest intensity that the human ear can detect sound. So we can barely hear a sound of 1 times 10 to the minus 12 watts per square meter. Now this is the reference level for the decibel system. The decibel system arose due to the fact that loudness and intensity are not exactly directly proportional in your linear way, so to speak. Let's say if you increase the intensity by a factor of 10. The loudness, which I'm just going to use L, the loudness will not increase by a factor of 10. It's going to increase by a factor of 2. So if you increase the intensity by a factor of 10, the sound wave is not going to sound 10 times louder. To us, it's only going to sound 2 times as loud or twice as loud. However, the intensity level will increase by an addition of 10. Not a multiplication of 10, but an addition of 10. So if you multiply the intensity by a factor of 10, the loudness will increase by a factor of 10, but the decibel level, the intensity level, will increase by an addition of 10. Let's use a table to describe the relationship between sound intensity, intensity level, and loudness. So I represents the intensity in watts per square meter. And then we're going to have the intensity level, which is measured in decibels. And then we're going to have the loudness. So let's start with the threshold of hearing, an intensity of 1 times 10 to the minus 12. The intensity level is 0 because that is the reference level. And let's assign it a loudness of 1. Now, if we increase the intensity by a factor of 10, the exponent will increase by 1. 10 squared is 100. 10 to the third is 1,000. 1,000 is 10 times more than 100, but the exponent differs by 1. 10 squared and 10 to the third, the exponent differs by 1, but the value differs by a factor of 10. The intensity level of this sound wave at that intensity will be 10 decibels, but it's going to sound twice as loud. So if we increase the intensity by another factor of 10, the sound level will increase by an addition of 10, and the loudness will increase by 2. So now it's 4 times as loud compared to this sound. So if we increase it by another factor of 10, this is going to increase by an addition of 10, and the loudness will be twice as loud as before. And I wrote negative 19, but I meant to write negative 9. Now, if we increase it by 10 again, this is going to increase by 10, and this is going to have a loudness of 16. Now, what if we increase it by a factor of 100? Let's say if we skip negative 7 and go to negative 6. So if you increase the intensity by a factor of 100, the intensity level will increase by an addition of 20. So it's going to be a value of 60. And the loudness will increase by a factor of 4. 16 times 4 is 64. Now, what if we increase it, let's say by a factor of 10 to the 4, which is 10,000? The decibel level will increase by 40, so it's now going to be 100, which means the loudness will increase by a factor of 2 to the 4th power, which is 16. 64 times 16 is 1,024. Now, if we increase it by another 100, I know I'm running out of space, so I'm going to write it in red. 1 times 10 to the 0 is simply 1. So at an intensity of 1 watt per square meter, the decibel level is going to be 120. Since we increase the intensity by a factor of 100, the decibel level will increase by an addition of 20, and the loudness will increase by a factor of 4. So it's going to have a value of 4,096. So at this level, the threshold of hearing, you can barely hear the sound. At a sound level of 20, it sounds like a whisper. At a sound level of 60 decibels, that's the sound of ordinary conversation. 100 decibels is basically the loudness of a siren. And 120 is basically the threshold of pain. Beyond 120, sound is painful. It's too loud. A sound source emits 36 joules of energy per minute. What is the power emitted by the sound source? Power is work divided by time. And work is basically how much energy is transferred. So you can think of power as being energy divided by time, which is joules divided by seconds. So we have 36 joules of energy emitted per minute or per 60 seconds. So therefore, the power transferred in units of watts is going to be 36 divided by 60, which is about 0.6 watts. So this means that every second, the sound source emits 0.6 joules of energy. So this is the answer to part A. Now what about part B? What is the intensity 5 meters away from the source? Intensity is power divided by surface area. So we have 0.6 watts being emitted, and a distance is 5 meters. So we need to replace r with 5. So you should get an intensity of 1.91 times 10 to the minus 3 watts per square meter. Now, what is the intensity level at this distance? We need to use this equation to calculate the intensity level. It's 10 times log of the intensity, which is 1.91 times 10 to the minus 3, divided by I naught, or I0, which is the intensity of the threshold of hearing, and that's 1 times 10 to the minus 12. 1.91 times 10 to the minus 3 divided by 1 times 10 to the minus 12 is 1.91 times 10 to the 9. If you take the log of that value, you should get 9.28 times 10 gives you a sound intensity level of 92.8 decibels. What is the intensity of a sound wave that has an intensity level of 75 decibels? So starting with this equation, we need to rearrange it to solve for the intensity. So let's go ahead and do that first. The first thing we should do is divide both sides by 10. So the intensity level divided by 10 is equal to log intensity over the threshold of hearing. Now let's review some things about logs. Let's say if you have log base A of B equal to C, you can convert it to exponential form by using this equation. A raised to the C power is equal to B. So for example, log 2 of 8 is equal to 3, because 2 to the third power is equal to 8. So knowing that, the base of log is always base 10 if there's no other number provided. So 10 raised to the b over 10 is equal to what's inside. That's I over I naught. So I divided by I naught is equal to 10 raised to the intensity level divided by 10. So now let's multiply both sides by I0. So the intensity is equal to the threshold of hearing multiplied by 10 raised to the intensity level divided by 10. So now that we have the equation, we can use it to answer the question. I naught is 1 times 10 to the minus 12. The intensity level is 75, and we're going to divide it by 10. 75 divided by 10 is 7.5. So we have 10 raised to the 7.5. So the final answer is about 3.16 times 10 to the minus 5 watts per square meter. So this is the intensity at an intensity level of 75. In this problem, we're given the intensity at a distance of 2 meters. What is the new intensity at a distance of 5 meters for part A? What equation can we use to solve a problem like this? So let's divide I2 by I1. The intensity is power divided by area. Now, because the source is the same, the power emitted by the source is the same. However, the distance from the source is different. So I'm going to put a subscript of 2 to show that it's associated with I2. So I1 is going to be P, because it's from the same source, divided by 4 pi R1 squared. So we can cancel the power, they're the same, and we can cancel 4 pi. So therefore, we have the equation I2 over I1 is equal to 1 over R2 divided by 1 over R1 squared. Now let's multiply top and bottom by R1 squared. If we do that, these two will cancel. And so we're going to have the equation I2 over I1 is equal to R1 squared divided by R2 squared. So from this equation, we can see that the intensity is inversely related to the square of the distance. The inverse relationship, you can see it due to the fact that the subscripts, they don't match. They're opposite to each other. And also, you can see the square for each of the R values. So you can see how it's similar to this relationship. So this is the formula that we need to use in order to solve it. We're looking for I2. I1 is 100. R1 is 2. R2 is 5. So let's cross multiply. A 100 times 2 squared. What is that? 2 squared is 4, and 4 times 100 is 400. And that's going to equal I2 times 5 squared. 5 squared is 25. 400 divided by 25 is 16. So this is equal to I2. So if we compare the two answers, the intensity decreased from 100 to 16. Anytime you increase the R value, the intensity will decrease. Whenever you move away from the source, the intensity will decrease. As you move away from a speaker, it's going to sound not as loud as before. Another way in which you can get the answer is by using the inverse square law. So notice that the distance increased from 2 to 5. If you take 5 and divide it by 2, you're going to get 2.5. So the distance increased by a factor of 2.5. So therefore, using the inverse square law, if we plug in 2.5 into R, 1 divided by 2.5 squared is basically 0.16, or 4 over 25. So therefore, the intensity should decrease by that factor. So multiply it by 0.16, which is 1 over 2.5 squared. 100 times 0.16 will give you the answer of 16. So now let's see if we can get the answer for the second part of the problem using the same process. So this time R2 is 1.3. So notice that we're closer to the source, which means that the intensity should be greater than 100. So the distance decreased by what factor? If we divide 1.3 by 2, it decreased by a factor of 0.65. So now if we plug that in to this relationship, 1 over 0.65 squared is about 2.367. So the intensity should increase by this value. So if we multiply by 2.367, it should be 236.7 watts per square meter. But let's use the formula to confirm that answer. So I2 divided by I1 is equal to R1 squared divided by R2 squared. So I1 is 100, R1 is 2, R2 is 1.3. So let's cross multiply. 1.3 squared is about 1.69. So we have 1.69 times I2, and that's equal to 2 squared times 100, which is 400. So I2 is just going to be 400 divided by 1.69. And you're going to get the same answer of 236.7 watts per square meter. So there's multiple ways in which you can get the same answer. But as you can see, because the distance was decreased, the intensity increased. It went up from 100 to 236.7. The intensity level of a certain sound source is 98 decibels at a distance of 12 meters. What is the intensity level at a distance of 150 meters? In the last example, we had an equation that connected the intensity with the distance. Now we need a new equation that connects intensity level with distance. So what can we do? How can we come up with an equation that can help us to solve this particular problem? So go ahead and pause the video and work out this example. Now we know that the intensity is equal to I naught times 10 raised to the intensity level divided by 10. We came up with this equation earlier in the video. So therefore, we could say that I2 divided by I1 is equal to, I2 is going to be I naught 10 raised to the B sub 2, the intensity level that corresponds to I2, over 10, and I1 is going to be I naught times 10 raised to the B1 divided by 10. So we can cancel I naught. And keep in mind, I2 over I1 is equal to R1 squared over R2 squared. So now let's ignore this portion of the equation and let's focus on these two since they are equal to each other. Now what is x to the 7th power divided by x to the 3rd power? In algebra, you've learned that it's x to the 4th power. It's 7 minus 3 is equal to 4. So knowing that, what is 10 b2 over 10 divided by 10 raised to the b1 over 10? So this is going to be 10, and we're going to take the top exponent and subtract it by the lower one, or the one on the bottom. So 10 b2 over 10 minus b1 over 10, which is simply the same as b2 minus b1 over 10. And that's equal to R1 squared divided by R2 squared. Now let's take the log of both sides. A property of logs allows us to take the exponent and move it to the front. So we could say that b2 minus b1 divided by 10 times log of 10 is equal to log R1 squared minus R2, or divided by R2 squared. Log of 10 is equal to 1. Keep in mind, if there's no base, then it's assumed to be a 10. Log base 10 of 10 is 1. So this disappears. So b2 minus b1 divided by 10 is equal to log r1 squared divided by r2 squared. So now let's multiply 10 by both sides. So b2 minus b1 is equal to 10 log r1 over r2 squared. So now we can come up with our final equation. Let's add b1 to both sides. So b2 is equal to b1 plus 10 log r1 squared divided by r2 squared. So we know that b1 is 98 decibels. We're looking for b2. r1, the distance that corresponds to a sound level of 98 decibels, is 12 meters. r2 is 150 meters. So at this point, we just got to plug it into the equation. So b2 is going to equal b1, which is 98, plus 10 log r1, which is 12 squared, divided by r2, which is 150 squared. So if you type this in your calculator, log 12 squared divided by 150 squared is about negative 2.1938 times 10. So we have b2, which is going to be 98 plus negative 21.938. So if we combine those two numbers, you should get a 76 point, well, let's round it to 76.1. So this is the sound level at the new distance. And it makes sense. If we increase the distance, then the sound level should decrease. These two are always inversely related. So now you have an equation that relates the sound level to the distance. Let's try this one. A 65 decibel sound wave strikes a surface with an area of 3 times 10 to the minus 4 square meters. How much power is absorbed by the surface, assuming 100% absorption? Well, first we need to calculate the intensity. The intensity is equal to I naught times 10 raised to the decibel level divided by 10. So this is 1 times 10 to the minus 12 times 10 raised to the 65 divided by 10. So the intensity is 3.162 times 10 to the minus 6 watts per square meter. Now we know that intensity is equal to the power divided by the area. So intensity times area is equal to the power measured in watts. So we're looking for the power in part A. So that's going to be the intensity, which has the units watts per square meter, multiplied by the area, which is in square meters. So the unit square meters will cancel, giving us the unit in watts, which is the unit for power. So therefore, the surface absorbs 9.0 0.486 times 10 to the minus 10 watts. Now what about part B? How much energy in joules is absorbed in 4 hours? Now we know power is equal to energy divided by time. So the energy is basically the product of the power multiplied by time. And the unit watt is basically the number of joules per second. So the energy absorbed, well, first let's find how much time in seconds is equal to 4 hours. So let's convert hours into seconds. So there's 60 minutes in an hour, and there's 60 seconds in a minute. So it's 4 times 60 times 60. So we have 14,400 seconds. So now we can calculate the total energy absorbed. So it's going to be 9.486 times 10 to the minus 10 joules per second multiplied by 14,400 seconds. So these units will cancel. So the total energy absorbed is about 1.366 times 10 to the minus 5 joules. Now here's a question for you. If we increase the frequency of a sound wave, what happens to the intensity of a sound wave? Will it increase or decrease? It turns out that the intensity will increase if you increase the frequency. And if you increase the amplitude, the intensity will increase as well. But let's come up with an equation that describes the relationship between frequency, amplitude, and intensity. If you recall from the simple harmonic motion of springs, the total energy of the system is 1/2 times the spring constant times the square of the amplitude. In addition, the frequency of a spring is 1/2 pi square root the spring constant divided by the mass. Now we can use these equations because these equations describe simple harmonic motion, which behaves like a wave. Now, with the equation on the right, let's solve for k. So let's square both sides. F squared is going to be equal to 1/4 pi squared times k divided by m. So if we multiply both sides by 4 pi squared m, we'll see that k is equal to 4 pi squared times the mass times the square of the frequency. Now let's replace k with this portion of the equation. So therefore we could say that E is equal to 1/2 times 4 pi squared times m times f squared times a squared. Now we know that power is energy divided by time. But actually, before we use that, let's talk about the mass. Mass is equal to density times volume, because density is mass divided by the volume. Now let's draw a rectangle. And let's draw just a cross-sectional area of the rectangle. this area in which the wave passes through, the cross-sectional area, we'll call it S. And the length of the rectangle, or the height, we'll call it L. The volume of this rectangle is the area times the length. And we know that the distance that a wave travels is the speed multiplied by the time. So we can treat L as the distance that it travels. The length of that rectangle could equate to the distance because they're both measured in meters. So we could say that L is equal to Vt. So M, which is equal to density times volume, we can replace V with area times length. So the mass is the density times the cross-sectional area times the length, and then we can replace L with Vt. So the mass is the density times the cross-sectional area times the speed of the wave multiplied by the time. So therefore, the power of the sound wave, this should be capital P, is equal to the energy divided by the time. The energy is 1/2 times 4, which is 2, times pi squared times the mass, which we can replace M with this expression, the density times the cross-sectional area times the speed multiplied by the time, times the square of the frequency and the square of the amplitude. And we're going to divide it by T. So T cancels. So therefore, the power of a sound wave is equal to this equation. Now that we have the power of the sound wave, we could come up with an equation that tells us the intensity. The intensity is equal to the power divided by the area. In this case, the area, the cross-sectional area, is S. So if we divide this expression by S, the intensity is simply going to be 2 pi squared times the density times the speed of the wave times the square of the frequency and the square of the amplitude. So from this equation, we could see that intensity is directly proportional to the square of the frequency. It's also directly proportional to the square of the amplitude. So what this means is that if we increase the frequency, let's say by a factor of 2, because it's squared, the intensity will increase by a factor of 4. Now the same is true for the amplitude. If we increase the amplitude, let's say by a factor of 3, 3 squared is 9, so the intensity will increase by a factor of 9. So we can come up with this equation. The ratio of the intensities is equal to the square of the ratios of the frequencies. So it's equal to f2 squared and f1 squared. Likewise, the same is true for the amplitude. The ratio of the intensities is equal to the square of the ratio of the amplitudes. So you might be wondering, what exactly is the amplitude? A sound wave is basically a pressure wave, and it can displace air. If we plot the displacement of air on the y-axis and time on the x-axis, we're going to get a sine wave. Let's say the displacement is 0 on the x-axis. The peak of the wave might be something like 0.001 centimeter. It's very small. And over here, it could be like negative 0.001 centimeter. So the amplitude A is really the displacement of the air molecules. And it's usually measured in meters, though, if you're going to use the equation. And frequency Now let's work on some problems. Calculate the displacement of air molecules for a sound wave having a frequency of 1500 Hz at an intensity of 4.2 times 10 to the minus 6 watts per square meter. And we're given the density of air. So we know the equation is the intensity is equal to 2 pi squared times the density times the velocity times the square of the frequency times the square of the amplitude. So we have the amplitude already. That is actually we're looking for the amplitude. The displacement of air molecules is the amplitude A. We have the frequency and we have the density. And we have the intensity. So I is 4.2 times 10 to the minus 6. That's equal to 2 pi squared. The density is 1.29. That's the density of the medium in which sound travels through, in this case air. The speed of sound in air is 343 meters per second. The frequency is 1500. Now let's solve for A. Two pi squared times 1.29 times 343 times 1500 squared is about 1.965 times 10 to the 10. So let's divide both sides by that number. So 4.2 times 10 to the minus 6 divided by 1.965 times 10 to the 10. That's equal to 2.137 times 10 to the minus 16. And that's equal to A squared. So to solve for A at this point, we need to take the square root of both sides. So the amplitude, which is the displacement of the air molecules, that's going to be about 1.462 times 10 to the minus 8 meters. A 2,500 Hz sound wave traveling in air has a displacement amplitude of 750 nanometers. The density of air is 1.29 kilograms per cubic meter. What is the intensity of the sound wave? So let's make a list of what we have. So we have the frequency. It's 2500. We have the amplitude. It's 750 nanometers. But to use the equation, we need to convert it to meters. 1 nanometer is equal to 1 times 10 to the minus 9 meters. So the amplitude is simply 750 times 10 to the minus 9 meters. Just replace the unit nm with 10 to the minus 9 meters, and you should be fine. Now we know that the density of air is 1.29 kilograms per cubic meter. And the speed of sound in air, we're going to assume at 20 degrees Celsius, is 343 meters per second. So therefore, we can use this equation to find the intensity. So it's equal to 2 pi squared times the density of air times the speed of sound times the square of the frequency times the square of the amplitude. So that's going to be 2 pi squared times p, which is 1.29, times the speed, which is 343, times the square of the frequency, 2500 squared, and the square of the amplitude, 750 times 10 to the minus 9 squared. So basically, you can type this in exactly the way you see it in your calculator. So you should get 0.03 watts per square meter. Now that we have the intensity, we can find the answer to part B. We can calculate the intensity level. And we can do that using this equation. The intensity level in decibels is basically just 10 times the log function of the intensity divided by the reference level, or the reference intensity. So all we got to do is replace I with this number. So the intensity is 0.03071. The reference intensity is 1 times 10 to the minus 12. Log 0.03071 divided by 1 times 10 to the minus 12 is about 10.487. And if we multiply this by 10, we're going to get a sound intensity level of 104.9 decibels. And that is it for this problem. Well, let's try this one. If the frequency of a sound wave is tripled, and if the amplitude is quadrupled, by what factor will the intensity increase? So let's write the equation first. Intensity is equal to 2 pi squared times the density times the velocity times the square of the frequency times the square of the amplitude. So we know that intensity is directly proportional to the square of the frequency. So that means that if we triple the frequency, if we increase it by a factor of 3, the intensity will increase by a factor of 9, because 3 squared is 9. And if we increase the amplitude by a factor of 4, the intensity should increase by a factor of 4 squared, or 16. And 9 times 16 is 144. So the intensity should go up by a factor of 144. Another way to get the same answer is to simply plug in the numbers into the equation. Everything that is held constant, which is this portion of the equation, replace it with a 1. So it's going to be 1 times 3 squared, because the frequency was tripled, times 4 squared. So that's going to be 9 times 16, which is 144. So that's the answer to part A. The intensity increases by 144. Now what about part B? By how many decibels will the intensity level increase? So let's say our reference level, or our reference intensity, has a value of 1 times 10 to the minus 12. The intensity increased by a factor of 144. So if we multiply 144 by 1 times 10 to the minus 12, you should get 1.44 times 10 to the minus 10. And now, let's calculate the sound level at that intensity. Keep in mind, the sound level at the threshold of hearing, at this reference level, is equal to 0. So if we could find the sound level at this new intensity, we could see by what factor, or by how many decibels, the intensity level increased. So let's use the equation. The sound level is going to be 10 times log of the intensity level, which is 1.44 times 10 to the minus 10, divided by the reference intensity, which is 1 times 10 to the minus 12. If you divide these two numbers, you're going to get this number, 144. So log of 144 is 2.158, and if we multiply by 10, we're going to get a sound level of 21.58. So the sound level increased by 21.58 decibels. That's the answer to part B. Now, before we can solve problems associated with organ pipes, whether if they're closed or open, we need to review standing waves and waves on a string. So let's say if we apply a force to produce a wave on a string, we can calculate the velocity of this wave using this equation. It's equal to the square root of the tension force divided by the linear density of the string that carries the wave. M is the mass of the string, L is the length. So using that equation, you could find the speed of the wave or the tension force required to produce a wave with a certain speed. Now let's say if we have a string attached to two ends or two fixed supports. L is the length of the string. And we can apply a force to produce a standing wave. A standing wave is basically a wave that appears to stand in place. It appears not to be moving, even though it is moving. Now there's different standing wave patterns that we can produce. But before we go into that, you need to know that this is one complete wave. A wave that looks like this has a length of one wavelength. So here we have two cycles. So this wave has a length that is equal to twice the wavelength of a wave. So let's say if we have one loop. This one loop corresponds to half of a wavelength, just this portion of the wave. So that loop has a length of L, and it's equal to 1/2 the wavelength. Now I'm going to put a subscript of 1 to correspond to the fact that it only has one loop, so N is equal to 1. Now let's say if there's two loops. It's going to look like this. So N is 2. Notice that for two loops, it's equal to one wave. That's one cycle, which has a length of one wavelength. So L is equal to lambda. But I'm going to write it as 2/2, so you can see a pattern. 2/2 is basically 1. Now let's say if we have 3 loops. So L is equal to 1.5 times the wavelength, or 3/2. So based on this pattern, we can come up with an equation. We can say that L is equal to N times the wavelength with a subscript of N divided by 2. As you can see, this 2 does not change. However, the number on top changes. 1, 2, 3. So basically, it corresponds to the number of loops, which N represents the number of loops. Now, if we solve for L, not L, but lambda, we're going to get this equation. If we multiply both sides by 2, it's going to be 2L. And if we divide by N, 2L over N is equal to lambda N. So this is another equation that you want to use whenever you have the length of the string and if you want to find the wavelength. Now, in addition to that, there are some other equations that we can get. We'll talk about them soon, but let me show you something else. Let's say if the frequency that corresponds to this particular standard wave pattern, let's say it's 100 hertz. This is known as the fundamental frequency, or the first harmonic. The second harmonic, or the first overtone, has twice the frequency. It's 200 hertz. The third harmonic is 300 hertz. This is the second overtone. The fourth harmonic will be 400 hertz, which is the third overtone. So as n increases, that is, as the number of loops increases, the frequency will increase, but the wavelength will decrease. So let's say that at a certain length and at a certain speed, let's assume that the wavelength is 1 meter. So the wavelength for a standard wave with 2 loops is going to be half of a meter, or 0.5. If there's 3 loops, it's going to be 1/3. So notice that the wavelength is decreasing. So as you can see, you can find any frequency using this equation. Fn is equal to n times the fundamental frequency. You just multiply by n. Now you can find the wavelength for any standard wave pattern if you know the wavelength of the fundamental. Instead of multiplying by n, you need to divide by n. Now let's talk about how to derive these equations. So keep in mind that lambda n we said was 2L divided by n. And we know that wavelength times frequency is equal to the speed of the wave. If we solve for frequency, the frequency is going to be the speed divided by the wavelength. So the frequency for any fundamental, or for any harmonic, is the speed divided by the wavelength that corresponds to that particular harmonic. So I'm going to write it as Fn is going to be v over 1 times 1 over lambda n. Now, if lambda n is 2L over n, 1 over lambda n is the reciprocal of this fraction. So therefore we have this equation, v times n over 2L. So this gives us another useful equation. We could find the frequency of any harmonic if we know the speed and the length. It's n times v divided by 2L. Now going back to this equation, lambda n is 2L divided by n. So lambda 1 is simply 2L over 1, which is 2L, which means that we can replace 2L with lambda 1. Now I'm going to write it like this, n over 1 times v over lambda 1. Now, as we said before, frequency is the speed divided by lambda n. So f1 is basically v divided by lambda 1. So notice we have v over lambda 1. That's equal to f1. So we now have the equation Fn is equal to n times f1. Now from that equation, we're going to get another equation. So the wavelength times the frequency is equal to the speed. Therefore, the wavelength is equal to the speed divided by the frequency. And 1 divided by the wavelength is the reciprocal of this fraction. It's the frequency divided by the speed. So from this equation, I'm going to divide both sides by v. So Fn divided by v is equal to n times f1 divided by v. One over lambda n is equal to Fn divided by V. So we can replace this with 1 over lambda n. So therefore, we could also say that 1 over lambda 1 is equal to F1 over V. All we did is we replaced n with 1. So F1 over V is 1 over lambda 1. So we have 1 over lambda n is equal to n over lambda 1. Now, if we take the reciprocal of both sides of the equation, we get this equation. Lambda n is equal to lambda 1 divided by n. Now let's go back to our standard wave pattern. Let's say if there's 3 loops. You need to know the difference between nodes and antinodes. These are the nodes. That's where the amplitude is 0. So for 3 loops, notice that the number of nodes is equal to n plus 1. So basically we have 4 nodes. Now the antinodes is where you have maximum displacement, or the amplitude is at a max. The number of antinodes turns out to be simply equal to the n value, or the number of loops. So in this case we have 3 antinodes. So make sure you know that too. Now sometimes you might encounter a word called octave. So let's say if you have a frequency that's 300 hertz. If you want to find a frequency that is an octave higher, I'm just going to put O with an arrow going up. So if it's 1 octave higher, the frequency is twice the value. You simply multiply it by 2. If it's an octave lower, the frequency is half of 300. You divide it by 2, so it's going to be 150. So when you hear the word octave, an octave that's higher is simply the next multiple of a number. Now, we went over a lot of equations at this point, so let's write down a list of the important equations that you need to know. So the first one, you've seen this already. The speed of a wave is equal to the wavelength times the frequency. So let's say if you have the wavelength of the third harmonic, you need to use the frequency of the third harmonic in order to get the speed. So the n values have to correspond to each other. Now you can also find the speed if you know the tension force, the mass of the string, and the length of the string. Keep in mind, the mass per unit length ratio is known as the linear density. Now we know that the frequency of any harmonic is basically n times the fundamental frequency, or the frequency of the first harmonic. And the wavelength of any harmonic is simply the wavelength of the fundamental divided by n. Now you can find the wavelength of any harmonic if you know the length of the string and also the number of loops in the standard wave pattern. And you can also find L using this equation. L is going to be the number of loops times the wavelength divided by 2. And finally, you can calculate the frequency if you know the number of loops and the speed and also the length of the string. So write down these 7 equations because it's going to be useful for the next few problems that you're about to solve. A tension of 300 newtons was applied to a 0.25 kilogram string that has a length of 3 meters. What is the velocity of the wave produced? So the equation that we need is this equation. First, let's calculate the linear density, which is the mass divided by the length. So the mass of the string is 0.25 kilograms, and it's 3 meters long. So the linear density is 0.083 repeated. kilograms per meter. So now let's find the velocity of the wave. So it's the tension force of 300 newtons divided by the linear density. So the velocity is roughly about 60 meters per second. That's how fast the wave is moving. Now what about part B? What is the fundamental frequency? And what is the frequency of the first three overtones? That's what I meant to say. Now, the equation that we can use to find the fundamental frequency is this equation. Fn is equal to Nv divided by 2L. Keep in mind, for the fundamental frequency, n is 1. So we're looking for f sub 1, where we have one loop in the standard wave pattern. So we have the speed, which is 60 meters per second, and we know the length of the string, which is 3 meters. 2 times 3 is 6, 60 divided by 6 is 10. So the fundamental frequency is 10 hertz. Now that we have the fundamental frequency, we can use this equation to find the first three overtones. The first overtone is basically the second harmonic, which is 2 times the fundamental, so it's going to be 20 hertz. The second overtone, which is the third harmonic, is 10 times 3, that's going to be 30 hertz. And the third overtone, which is the fourth harmonic, is 10 times 4, which is 40 hertz. So that's all you got to do for part B. Now what about part C? What is the wavelength of the second overtone? Now there's many different ways in which we could find this answer. The second overtone corresponds to the third harmonic. The frequency of the third harmonic we said is 30 hertz. So first we can use this equation. The speed is equal to the wavelength times the frequency. So the speed is equal to the wavelength that corresponds to the third harmonic times the frequency of the third harmonic. So 60 is equal to lambda 3 times the frequency of 30. So the wavelength for the third harmonic, or the second overtone, is 60 divided by 30, which is 2 meters. Now let's see if we can confirm that answer with another equation. The other equation that we could use is this one. Lambda n is equal to 2L divided by n. So lambda 3 is simply 2 times the length, which is 3 meters. L is 3. And n is basically the subscript value, which is 3. So we can cancel the 3's and we get an answer of 2. So as you can see, there's multiple ways in which you can get the right answer. So make sure you know the equations and how to use them. Try this problem. The frequency of the fourth harmonic is 100 hertz. What is the frequency of the 11th harmonic? So we know that F4 is equal to 100. And our goal is to find the value of F11. So first, let's calculate the fundamental. Using the equation Fn is equal to n times F1. So F4 is 4 times the value of F1. So if F4 is 100, that means that the fundamental frequency is 100 divided by 4, which is 25 hertz. So now that we have the fundamental frequency, we can find the 11th harmonic using this equation again. So F11 is simply 11 times the fundamental. So it's 11 times 25. So what is the value of 11 quarters? 11 quarters is $2.75. So 11 times 25 is 275. So this is the frequency of the 11th harmonic. Let's try this one. How many nodes and antinodes are present in a standard wave with 5 loops? So let's draw a picture first. So here we have 5 loops. the number of nodes is equal to n plus 1. So notice that we have 6 nodes. 5 plus 1 is 6. The number of antinodes is always equal to the number of loops, which is 5. So the number of antinodes is always equal to n. And that's all you got to do for this question. In this problem, we're given the frequency of the C note, which is 262 Hertz. And we want to find the frequency that is 1 octave higher than this number. To do that, simply multiply by 2. 262 times 2 is 524 Hertz. So this is the answer to the question. Now, if we want to find another frequency that's 1 octave higher than 524, multiply by 2 again, and this will be 1048. So this number is 2 octaves higher than 262. If we want to get a number that's 1 octave lower than 262, divide by 2. So this is going to be 131. But the answer to this problem is 524. The fundamental wavelength of a standing wave on a 0.35 kilogram string is 0.5 meters. What is the wavelength that corresponds to the first 2 overtones? So we have lambda 1, which is 0.5 meters. The first overtone is basically the second harmonic, so we got to find lambda 2. So let's use the equation lambda 1 divided by n. So this is going to be 0.5 divided by 2, which is 0.25 meters. So that's the wavelength that corresponds to the first overtone. The wavelength that corresponds to the second overtone, which is the third harmonic, is lambda 1 divided by 3. So that's 0.50 meters divided by 3. So this is going to be 0.167 meters. So now that we have that value, what about part B? How can we find the length of the string? What equation can we use? The equation that we need is this one. L is equal to n times lambda n divided by 2. So let's use the fundamental wavelength, lambda 1, which means n is 1. So it's 1 times 0.5 divided by 2, which is 0.25 meters. So that is the length of the string. Now what about part C? What tension force is required or necessary to produce a wave with a speed of 50 meters per second? So let's start with this equation, but let's rearrange it to calculate the tension force. So let's square both sides. V squared is equal to F divided by m over L. Now I'm going to multiply the top and the bottom fraction by L so that these cancel. And so we can see that V squared is equal to F times L divided by m. Next, I'm going to multiply both sides by m. So F times L is equal to mv squared. Now to get F by itself, I'm going to divide by L. So the tension force is the linear density times v squared. So now let's plug in what we have into the formula. So the tension force is equal to the mass, which is 0.35 kilograms, divided by the length of the string, which is 0.25 meters, times the square of the speed, which is 50 meters per second. So 0.35 divided by 0.25 is 7 over 5, which is 1.4, times 50 squared, and that's going to be 3,500. So the tension force is 3,500 newtons. Now, what is the frequency of the third harmonic? What different ways can we use to find it? So keep in mind the wavelength of the third harmonic is 0.5 divided by 3, which we said is about 0.167 meters. So to find the frequency, we can use this equation. V is equal to lambda 3 times F3. So the speed is 50. Lambda 3 is 0.167. So F3 is going to be 50 divided by 0.167, which is approximately about 299.4. Now this, of course, is a rounded answer. So if we type in 50 divided by 0.166667, because it's really 0.16 repeating, it's really about 299.99. So we can say that it's really supposed to be 300. That's the exact answer. Now, what other equation can we use to calculate the frequency of the third harmonic? What would you say? The other equation that we can use is this one. F3 is going to be n, which is 3, times the speed, which is 50, divided by 2L, and L is 0.25. 50 times 3 is 150. 2 times 0.25 is 0.5. 150 divided by 0.5 is 300. The wavelength of the third harmonic is 0.6 meters. What is the wavelength of the sixth harmonic? So we know that lambda 3 is 0.6 meters. What is lambda 6? So the equation that we need is this one. First, we need to find the fundamental wavelength. So if we multiply both sides by n, lambda 1 is equal to n times lambda n. So lambda 1 is basically 3 times lambda 3. So that's 3 times 0.6, which is 1.8 meters. So the fundamental wavelength is 1.8 meters. Now that we have that, we can find lambda 6 using this equation. So lambda 6 is going to be lambda 1 divided by 6, which is 1.8 meters, over 6. If 18 divided by 6 is 3, 1.8 divided by 6 is 0.3. So the final answer is 0.3 meters. The wavelength of the third harmonic is 1.5 meters. So lambda 3 is this number. And we have the frequency of the fifth harmonic, which is 200 hertz. What is the speed of the wave? At this point, we cannot use this equation, lambda f is equal to v, because the subscripts do not match. So what should we do in this case? How can we solve this problem? The best thing to do is to find the fundamental wavelength and frequency. We know that Fn is equal to n times F1. So F5 is equal to 5 times F1. F5 is 200, and F1 is 200 divided by 5, which is 40 hertz. Now we know that lambda n is equal to lambda 1 divided by n, which means lambda n times n is equal to lambda 1 if you multiply both sides by n. So lambda 3 times 3 is lambda 1. So 1.5 times 3 is lambda 1, which is 4.5 meters. So now that we have the wavelength and the frequency that corresponds to the same subscript, we can now find the speed. So we just got to multiply these two values. So 4.5 times 40 is going to give us the speed. And that's going to be 180 meters per second. Now let's talk about pipe organs when they're open at both ends and when they're closed at one end. But let's talk about how the shape looks like if it's open at both ends. So we're going to have one node to correspond to the fundamental frequency. And the standard wave pattern looks like this. This is equal to a standard wave pattern with one loop. Notice that this is the left side portion of the loop on the right, and this is the right side portion. So since we have one loop, n is equal to 1. Therefore, the length is equal to 1/2 of the wavelength. Keep in mind, a wavelength is the length of two loops. Since we have one loop, the length is half of the wavelength. Now what about if we have two nodes? How is it going to look like? It looks like that. Now how many loops do we have in this picture? So notice that here we have half a loop, we have a full loop, and another half. So we have a total of 2 loops. So we're going to say n is basically 2. So the length is going to be equal to the wavelength. 2 over 2 is 1. Now let's see how it's going to look like if we have 3 nodes. So this time n is 3, and L is 3 over 2 times the wavelength. This is lambda 1, lambda 2, lambda 3. So this is the fundamental wave, or the first harmonic. This is the second harmonic, which is the first overtone. This is the third harmonic, which is the second overtone. So we can write a general equation for L, just like we did before for the standing waves. We can say that L is n times the wavelength divided by 2. And if we want to solve for the wavelength, it's going to be 2L divided by n. And the frequency, Fn, is going to be NV over 2L. So for a pipe that's open at both ends, the equations that we've used for standard wave patterns applies to this as well. N could be anything. It could be 1, 2, 3, 4, and so forth. Now the other equations still apply. For example, Fn is still n times F1, and lambda n is still lambda 1 divided by n. Now keep in mind that these waves that you see here for an open organ pipe, the waves that you see represent the displacement of air. At the open end, notice that we always have an antinode. The reason for that is because air is free to move at the end. If we had a closed end, it would be a node at that point because air is not free to move at the closed end of a tube. So let's go ahead and talk about an organ pipe that is closed at one end. So for the displacement of air, we are always going to have a node at the closed end. So this is going to look something like this. So notice that this is not even a full loop. This is half of a loop. Keep in mind, 2 loops is equal to 1 wavelength. So half a loop is 1/2 of a wavelength. Therefore, what we have is a quarter of a loop. And keep in mind, this picture represents the length of the pipe, which is L. So we can say that L is 1/4 the wavelength. So we always have a node at the closed end. And for the displacement of air, we always have an antinode at the open end, since air can move freely at that point. Just keep those things in mind. So now, let's draw the next overtone. So this time, we're going to have two nodes. So at the open side, it's going to be an antinode. And at the closed side, we're going to have a node. So it looks like this. So this is one loop, that's half a loop. So we have 1.5 loops. 1 plus 1/2 is 3/2 as a fraction. So what is the length of this particular picture? So we said that one loop is half a wavelength. And half a loop is 1/4 of a wavelength. 1/2 plus 1/4 is 3/4. Now, something that you need to be careful with is that the end value here is 1. But for this one, it's not 2, it's 3. So this is the first harmonic. This is the third harmonic. There's no second harmonic or fourth harmonic when it's closed at one end. N can't be 2, 4, or 6. N can only be odd numbers like 1, 3, 5, and 7. So keep that in mind when you're dealing with the closed end organ pipe. So now let's draw the next one. So the next one is going to have 3 nodes. And we're still going to have an antinode at the end. So it's going to look like that. Keep in mind, each loop represents 1/2 of a wavelength. So this is half of a wavelength, plus another half of a wavelength, plus 1/4 of a wavelength. 0.5 plus 0.5 is 1, and 1/2 is 0.25. 1.25 as a fraction is 5/4. Basically, multiply the top and bottom by 4, and you'll get 5/4. So therefore, we could say that the length is equal to 5/4 of the wavelength. And for this picture, N is equal to 5. Now, given these 3 equations that we have here, how can we write a general equation that describes L in terms of the wavelength? So notice that L doesn't change, the lambda symbol doesn't change, and the 4 on the bottom doesn't change. The only numbers that are changing is the numerator and the subscript, so we can replace that with N. Therefore, the general equation is this: L is equal to N times lambda sub N divided by 4. So that's whenever you have an organ pipe that is closed at one end, such as the clarinet. The flute would be considered an open pipe or an open tube. Now, if we're solving for lambda, it's going to be 4L divided by N. So that's another equation that you want to know. Now, what about the frequency? Lambda times the frequency is equal to the speed. And lambda is 4L over N. So solving for F, we can say F sub N is the velocity times N divided by 4 times the length. So that's how you can find the frequency for any harmonic. Now the other equations still apply. Fn is still N times F1, and lambda N is still lambda 1 divided by N. Now I want to talk about the pictures or the wave patterns for the displacement of air and compare it to the pressure of air. So first, let's go over the open tube. So for the displacement of air, where we had only one node, we said the picture looked like this. As you can see, there's an antinode at the end. So I'm going to write AN for antinode, and there's a node in the middle. Now, if you're dealing with the pressure of air for an open tube, it looks like this. Notice that the node is at the open end, and the antinode is inside. It's different. The reason why we have an antinode outside for the displacement of air is because air can move freely there. Whereas in the case of pressure, the reason why we have a node is because it's open to the atmosphere. It doesn't alternate there. But on the inside, the pressure can alternate. Now, what if we have a closed tube, one that's closed on one side? Now, for the displacement of air, we drew the picture. We said that there's a node on the closed end and an antinode on the open end. And so it looked like this. So here's the node, and here is the antinode. So for the displacement of air, it's free to move at the open side. So we have an antinode. But air is not, it doesn't move freely at the closed end. So we have a node. In the case of pressure, the opposite is true. We're going to have a node on the outside and an antinode at the closed end. So at the closed end, the pressure can oscillate, and that's why we have an antinode. It can oscillate above and below the atmospheric pressure. Now what about the next harmonic, or the next overtone? Let's draw it for an open tube and then we'll draw it for a closed tube, or a tube that's closed at one end. So this time we're going to have two nodes, and we've seen this picture. So for the displacement of air, keep in mind we're always going to have an antinode whenever the tube is open. Let's do that again. So it looks something like that. Now what about for pressure? So we're going to have a node at the end. But this time we're going to have 3 nodes instead of 2. We need to have a total of 2 loops. So it looks like this. Keep in mind this is half a loop, 1 loop, and a half. Here we have 1 and 1, which is 2 loops total. Now for the closed tube, we can't really do a second harmonic because the end values have to be odd. So we're going to have to draw the picture for the third harmonic. Now for the displacement of air, there's going to be 2 nodes. So it's going to look like this. So that's for the third harmonic, where n is 3. For this one, n is 2 when it's open. Now, what about for the pressure? So we're going to have a node at the end and an antinode at the closed end, but a node at the open end. So it's going to look like this. In both cases, we have 1.5 loops, 1 and a half and 1 and a half. So the number of loops should still be the same. But for pressure, you always have a node at the open end and an antinode at the closed end. For the displacement of air, you always have an antinode at the open end and a node at the closed end. So let's start with this problem. We're looking for the fundamental frequency and the first two overtones. We're given the length of the pipe. So L is 1.3 meters. And we're dealing with a pipe that's open at both ends. So what equation can we use to find the fundamental frequency? The equation that you want to use is this one. Frequency is equal to n times the speed of sound divided by 2L. So the first harmonic is going to be 1 times 343 divided by 2 times 1.3. So it's 343 divided by 2.6. And so the frequency is going to be, I'm going to round it to the nearest whole number. So it's about 132 hertz. It's really 131.9. Now what about the second harmonic? So we can use the equation Fn is equal to n times F1. So it's simply going to be 2 times 132, which is 264 hertz. The second harmonic is the first overtone. The third harmonic is the second overtone, so that's going to be 3 times 132, which is about 396 hertz. Now what if the pipe is closed at one end? What is the equation to find the fundamental frequency? If it's closed at one end, you want to use this equation. Fn is equal to n times V divided by 4L. Now keep in mind, if it's closed at one end, we can only use odd numbers for n, no even numbers. So the fundamental frequency is F1. That's going to be 1 times the speed divided by 4L, or 4 times 1.3. 4 times 1.3 is about 5.2, and 343 divided by 5.2 is about 65.96, which I'm going to round and say is 66 hertz. So the first overtone is the third harmonic, so be careful with that. So it's 3 times 66, which is about 198 hertz. Now the second overtone is the fifth harmonic. So that's 5 times 66, which is 330. What is the length of a closed organ pipe that emits a fundamental frequency of 262 hertz at 20 degrees Celsius? So we're looking for L. We have the fundamental frequency F1, which is 262, and at this frequency n is 1, and we know the speed of sound is 343. So once again, we can use this equation. NV over 4L, not 2L, because we have a closed organ pipe. So to solve for L, it's going to be NV divided by 4 times the frequency. So N is 1, V is 343, and F is 262. 4 times 262 is 1048. 343 divided by 1048 is about 0.327 meters. So that's how long the closed organ pipe should be. So let's try this one. The length of the flute is 79 centimeters, which if we convert it to meters, we need to divide by 100. That's 0.79 meters. By the way, for each of these problems, feel free to pause it as soon as I start it, so you can get a chance to try it yourself. What is the fundamental frequency at 20 degrees Celsius? So a flute, is it considered to be an open tube or a closed tube? For the most part, a flute is an open tube. So the equation that we want to use is this one. It's NV divided by 2L. So we're looking for the fundamental frequency. N is 1. And at 20 degrees Celsius, the speed of sound is 343 divided by 2L. So 2 times 0.79, that's 1.58. 343 divided by 1.58 is equal to 217.1. So that's the fundamental frequency for part A. Now what about part B? What if the temperature is decreased to 5 degrees Celsius? So what would be the fundamental frequency of this cold flute? So the speed is going to change. The speed is dependent on the temperature. As mentioned before, the speed is 331 plus 0.6 times t. So 331 plus 0.6 times 5. That's about 334 meters per second. So now let's calculate the fundamental frequency using this equation again. So it's going to be n, which is 1, times the new speed of 334 divided by 2L. So it's 334 divided by 1.58. And that's about 211.4 hertz. So notice that as you decrease the temperature, the speed decreases. And as a result, the fundamental frequency of this musical instrument decreases as well. Likewise, if you increase the temperature, the speed of sound will increase and the frequency will increase. So at high temperatures, the flute is going to emit a higher pitch or higher frequency. At low temperatures, it's going to emit a low pitch or a lower frequency. Now let's talk about this equation. Notice that V and F are directly related since V is on top. So if you increase the speed of sound, the frequency will increase. The sound is going to have a higher pitch. It's going to sound more squeaky, so to speak. Now what about the length? Notice that the frequency is inversely related to the length of the instrument. If you increase the length, the frequency will decrease. And so it's going to have more bass. It's going to have a lower pitch. If you decrease the length, then you can increase the frequency giving it a higher pitch. So now let's answer part C. What is the fundamental frequency at 20 degrees Celsius if the flute was filled with helium? So what is the speed of sound in helium? In helium, it's about 1,000 meters per second, but it's really 1,005. You can round it to 1,000 if you want. L is about, it's still 0.79. So 1,005 divided by 1.58 is about 636 hertz. So that is the fundamental frequency. Now let's make sense of this number because it's much higher than the answers in part A and B. And we can see why. The speed of sound in helium is much higher than the speed of sound in air. So the frequency is significantly higher. And it makes sense because have you ever seen someone breathe in helium? How does their voice sound? Typically they have a higher pitch. Their voice sounds more squeaky, kind of like a chipmunk. And the reason for that is because sound travels much faster in helium than it does in air because helium is a lot lighter than air. And so they typically would have a higher pitch or more squeaky voice whenever someone breathes in helium. A 1.36 meter tube is open at both ends and resonates two successive harmonics of 375 and 500. What is the speed of sound in this tube? Now we know that we can use this equation. The tube is open, so it's going to be NV over 2L. and not 4L. So if we know the fundamental frequency, we could find the speed. So what is the fundamental frequency? Now let's assume that the fundamental frequency is 70. The second harmonic is 140. It's 70 times 2. The third harmonic is 3 times 70, which is 210. The fourth harmonic is 280. Notice that the difference is always 70. If you subtract F2 by F1, it's 70. F3 by F2, 210 minus 140 is 70. F4 minus F3 is 70 as well. So the difference between any successive harmonics will always give you the fundamental frequency. Therefore, we could say F1 is 500 minus 375. So the fundamental frequency is 125 Hertz, which means that the 375 is the third harmonic, because 375 divided by 125 is 3. The 500 frequency, or the one at 500 Hertz, that's the fourth harmonic, because 500 divided by 4 is 125. So now that we have the fundamental, what's the speed? To calculate n, if you want to rearrange the equation, it's going to be 2L times the frequency divided by n. That's going to be v. So it's 2 times the length of the tube, which is 1.36, times the fundamental frequency, which is 125, and n is 1. So the speed of sound is 340 meters per second. So that's the answer to part A. Now that we have that information, we can answer part B. What is the temperature of the air? We know the speed of sound is equal to 331 plus 0.6 times t. So 340 is equal to 331 plus 0.6 times t. If we subtract both sides by 331, 340 minus 331 is 9. And 9 divided by 0.6 is 15. So it's 15 degrees Celsius. An air pipe can produce successive harmonics at 252 and 315 Hertz. Is the pipe open or closed? So how can we figure this out? The first thing we need to do is find the fundamental frequency, which is the difference between the successive harmonics. So 315 minus 252 is equal to 63. Now keep in mind, if we have an open pipe, n could be anything. It could be even or odd. If we have a closed pipe, n can only equal odd numbers. So let's find out the n value for the harmonic at 252. So take that frequency divided by the fundamental and see what you get. 252 divided by 63 is 4. So that tells us that F4 is 252. That's the fourth harmonic. If we take 315 and divide it by 63, we're going to get 5. Because we have an even value, that tells us that the pipe is closed at one end. I take it back. I meant to say it's open at both ends, because it's even. We have an open pipe, not a closed pipe. So now that we know the pipe is open and not closed, how long is the pipe? So now we can choose which equation to use. So we need to use this one, NV over 2L, since the pipe is open. So F1 is 63, N is 1, V is 343 at 20 degrees Celsius, and we're looking for L. So 343 divided by 2 times 63 will give us the value of L. 2 times 63 is 126. 343 divided by 126 is about 2.72. So that's how long the pipe is. A 1.15 meter pipe in air can resonate at 222, 370, and 518, but not at any other frequencies between 222 and 518. What is the fundamental frequency? If the pipe is an open pipe, then 222 and 370 are successive harmonics. The fundamental frequency will be the difference between the two. If it's a closed pipe, that means that the successive overtones differ by 2 harmonics, which means that the fundamental frequency will be the difference between the two numbers divided by 2. So let's see if the fundamental frequency is simply 370 minus 222, or if it's 370 minus 222 divided by 2. 370 minus 222 is 148. By the way, if you take 518 minus 370, it's also 148. Now half of 148 is 74. So notice that 222 is not a multiple of 148. 222 divided by 148 doesn't give you a whole number, it's 1.5. Which means that 148 is not the fundamental frequency. 222 divided by 74 is a whole number, it's 3. 370 divided by 74 is also a whole number, that's 5. And 518 divided by 74 is 7. So that tells us that the fundamental frequency is 74 and that we have a closed pipe because the end values are all odd. None of them are even. So now that we know we have a closed pipe, we can use this equation to calculate the speed. So solving for V, it's going to be 4L times the frequency divided by N. So let's use the fundamental frequency of 74. So it's 4 times the length of the pipe, which is 1.15 meters, times the fundamental frequency, which N is 1 in that case. So if we multiply these three numbers, we should get 340.4 meters per second. So that's the speed of sound in this pipe. What is the fundamental wavelength of a 0.65 meter closed organ pipe and the wavelength of its first two overtones? So since the pipe is closed, we can use this equation. Lambda n is equal to 4L divided by n. So lambda 1, the fundamental wavelength, is 4 times the length of the pipe divided by 1. So it's 4 times 0.65, which is 2.6 meters. Now, because the pipe is closed, the end values can only be odd numbers, 1, 3, 5, and 7. So to find the next overtone, we need to plug in 3. And we can use the equation lambda n is simply lambda 1 divided by n. So it's going to be 2.6 divided by 3. And that's 0.867 meters. Now to find the second overtone, which is the fifth harmonic, it's 2.6 divided by 5. And that's about 0.52 meters. Now what about the second part of the problem? How long should the closed organ pipe be to produce a fundamental wavelength of 1.35 meters? So let's use this equation if we're looking for the length of the pipe. So the fundamental wavelength, where the n value is 1, the wavelength is 1.35, and then we just got to divide it by 4. So the pipe should be 0.3375 meters long. A 1.5 meter open organ pipe produces a fundamental frequency of 114 Hz. If the length of this pipe was decreased to 1 meter, what fundamental frequency will it produce? So for an open organ pipe, we know the fundamental frequency is NV divided by 2L. So because L is in the bottom of the equation, L and the frequency are inversely related. If you increase L, the frequency will decrease. F is inversely related to L. So if you double the length of the organ pipe, the frequency will be half of its original value. If you decrease L, F will increase. Since we decreased it to 1, we should expect a frequency that's higher than 114. So let's come up with an equation that relates F and L together. F2 divided by F1, where F2 is not the second harmonic, but just a different fundamental frequency. This is going to be NV over 2L2 divided by NV over 2L1. So NV are the same since we're dealing with the fundamental frequency. We can cancel 2, so we could say that F2 over F1 is 1 over L2 divided by 1 over L1. If you multiply top and bottom by L1, you're going to get this equation. F2 over F1 is equal to L1 over L2. The fact that the subscripts are opposite to each other shows the inverse relationship. So that's the equation that relates two frequencies to two different L values. So F1 is 114. We're looking for the new fundamental frequency. L1 is 1.5 meters. L2 is 1.0 meter. So if we cross multiply, 114 times 1.5 is about 171 hertz. And that's equal to 1 times F2, which is simply F2. So as you can see, if you decrease L, the frequency increases. So now what about the second problem? How long should the pipe be to produce a fundamental frequency of 80? So we're going to say F1 is 114, F2 is 80. L1 is 1.5. We're looking for the new L value. So F2 over F1, that's 80 over 114. L1 over L2, it's 1.5 over L2. Now let's cross multiply. So we have 80 times L2, and that's equal to 114 times 1.5, which is 171. So L2 is 171 divided by 80, and that's about 2.14 meters. So notice that we decreased the frequency from 114 to 80, so the L value should increase, and it did, from 1.5 to 2.14. The next thing we need to talk about is interference and the principle of superposition. Waves are additive. Let's say if we have a wave that looks like this, and it has an amplitude of 1. And let's say there's another wave that's in phase with the first one, but has a larger amplitude of 2. Because these two are in phase, they will add together to form a bigger wave with an amplitude of 3. This is known as constructive interference, whenever two waves combine to form a larger wave. And it occurs anytime when they're in phase. But what about when they're out of phase? So let's say if the first wave is the same. It has an amplitude of 1. And let's say the second wave is out of phase with the first one. But let's say that it has an amplitude of -2. According to the principle of superposition, these two waves will add, and so 1 plus -2 is -1. So destructive interference occurs at this point because the amplitude is less than what it was here. Whenever two waves either weaken their amplitudes or if they cancel out, if they're out of phase, destructive interference occurs. Now let's say if the second wave had the exact same amplitude but in the opposite direction, then these two waves will completely cancel out, and so the sum would be 0. So we would have nothing. That's another example of destructive interference. Now for destructive interference to occur, the distance between two waves must differ by half a wavelength. It could be 1/2 a wavelength, it can be 1.5 or 2.5, but they must differ by 1/2 of a wavelength. So if you want a general equation, it's like n plus 1/2 times a wavelength, where n is an integer such as 0, plus or minus 1, plus or minus 2, and so forth. Now for constructive interference to occur, the distance between two waves must either be equal or differ by a wavelength. It could differ by 1 wavelength, by 2 wavelengths, or by n wavelengths, where n is 0, plus or minus 1, plus or minus 2, and so forth. Now let's say if we have two speakers that emits a sound wave, and we have a person standing at this position. Let's call this speaker A and speaker B. Let's say that the distance between speaker A and B is about 3 meters. And these two speakers, let's say that they emit a sound with a frequency of 1400 hertz. Actually, let's say it's less. Let's say it's 500 hertz. And that's both speakers, speakers A and B. They emit the same sound. Now, how far away should this person be from speaker B in order for destructive interference to occur? Now, there's many values, but what are some values in which he has to be from speaker B in order for destructive interference to occur? What would you say? How would you begin? Now, the first thing you need to do is to find the wavelength. And we're going to use the speed of 343 meters per second. So let's use the equation wavelength times frequency is equal to the speed. So the wavelength is the speed divided by the frequency. So it's 343 meters per second divided by 500. And that's about 0.686 meters. So let's say if this is not drawn to scale. If the distance between speaker B and a person, let's call it point C, if it's half of this number plus 3, destructive interference will occur. So 1/2 of a wavelength, which is 0.686 divided by 2, that's 0.343. If it differs by this number relative to 3, destructive interference will occur. So let's say if it's 3.343 meters, this person won't hear anything. The two waves produced by speaker A and B will cancel. Now let's say if it was 3 minus 0.343. Let's say if it's 2.657. Now based on the picture, the way it looks like, it should be more, because this distance is clearly greater than 3. But let's say if it wasn't drawn to scale, let's say if the person was over here or something, then this distance could be less than 3. But if it was 2.657, destructive interference will still occur. Also, if it differed by 1.5 of a wavelength, destructive interference will occur as well. So if we multiply 0.686 times 1.5, we would get 1.029 meters. So if you add 3 to it, destructive interference will occur at 4.029 meters, or if you take away that number from 3 minus 1.029, that's 1.971 meters. Destructive interference will occur at that point too. So go ahead and try this problem. So we have 2 speakers. And this time we're going to put the person in the middle. So the person stands 5 meters away from one of the speakers. Let's say it's this one. And what is the nearest distance, or the distance nearest to 5, that the person must stand from the other speaker in order for constructive interference to occur? Well, the first thing we need to do is find the wavelength. So the wavelength times the frequency is equal to the speed. So lambda is going to be the speed divided by the frequency. So this time it's relatively small since we have a higher frequency. 343 divided by 1500 is about 0.229 meters. Now the next thing you want to do is find out how much half of a wavelength is. This is for part B, by the way. So half of 0.229 is about 0.1145. But I'm going to round it and say 0.115. Now, for constructive interference to occur, it has to differ by at least 1 wavelength. Now, we want the distance nearest to 5, so we don't want to use 2 or 3 wavelengths, even though constructive interference can occur at those points. But we want the closest distance to 5. So for part A, all you got to do is add and subtract a wavelength from 5. So one answer is 5.229. The other answer is 5 minus 0.229, which is 4.771 meters. So that's how far the person should be from the second speaker in order for constructive interference to occur. Now for destructive interference to occur, the distance have to differ by half a wavelength. So it's going to be 5 plus or minus 0.115. So if we add the two numbers, it's going to be 5.115 meters. And if we subtract them, it's going to be 4.885. If we have 2 sources of sound where the frequency of the first sound is very close to the frequency of the second sound, then a beat frequency will be produced. So let's say if we have a frequency of 300 Hertz and 305, a beat frequency of 5 Hertz will be heard. What happens is, in the time of 1 second, these 2 sound waves will produce 5 points of constructive interference. And those 5 points of constructive interference is the frequency, or the beat frequency. So if the frequency is 5 Hertz, that means that it's 5 cycles per 1 second. So there's 5 points of constructive interference that occurs in a single second. The beat frequency is simply the absolute difference between the 2 frequencies. And it occurs whenever these 2 frequencies are very close in value. A tuning fork produces a frequency of 415 Hertz. It generates a beat frequency of 7 Hertz with another sound source. What are the possible frequencies generated by this sound source? So the beat frequency is the difference between the tuning fork frequency and the frequency of the other sound source. So therefore, the other sound source must be 7 Hz away from 415. So there's two things we can do. We can add 7 or we can subtract 7. So one possible frequency is 422 Hz and the other possible frequency is 408 Hz. So the sound source has to have one of these two frequencies. A speaker produces a beat frequency of 6 Hz with a 336 Hz tuning fork and a beat frequency of 8 Hz with a 350 Hz tuning fork. What is the frequency emitted by the speaker? So go ahead, take a minute and work on this example. So let's start with the 336 Hz tuning fork. So it produces a beat frequency of 6 Hz with the speaker. So that means we need to subtract 6 and add 6. 336 minus 6 is 330. And 336 plus 6 is 342. Now let's do the same with the other tuning fork, which is calibrated for a frequency of 350 Hz. It produces a beat frequency of 8 Hz with the speaker. So if we add 8, this is going to be 358. And if we subtract 8, 350 minus 8 is 342. So therefore, the number that agrees with both tuning forks is the right answer. So the speaker produces a frequency of 342. Perhaps you've noticed that as the siren of an ambulance truck, as it approaches you, it has a higher pitch, meaning a higher frequency. And as it moves away from you, the pitch sounds lower. It has like a lower frequency. This change in frequency that is detected by the observer or the listener is known as the Doppler effect. The frequency of the source remains the same. However, the frequency that you detect sounds different than the frequency of the source. And that shift in frequency due to motion is the Doppler effect. So why is it that when the source, let's call it S, moves towards you, the frequency that you hear is higher than that of the source? And as the source moves away from this person, the frequency that this person hears is lower than the frequency of the source. Why is that? Well, let's call this person John. Let's give him a name. And let's say that this person on the left, let's call her Sally. Now, when the source is at rest, John and Sally will hear the same frequency. Let's say the frequency is about 1,000 Hz. The distance between each circle represents the wavelength. So when a source is not moving, notice that the circles are evenly apart. So John and Sally will hear the same frequency. But now let's say if the source is moving to the right. How would that affect the waves? The waves are going to look like this. On the right side, the waves are going to be close to each other, but on the left side, it's going to be further apart. My circles aren't perfect, but the idea is that as the source moves towards the right, notice that the wavelength, the distance between the wave crests, is decreasing. It's less than what it is on the left side. And as the wavelength decreases, the frequency increases. The reason why the wavelength is decreasing is because think of the distance between the source and John. As the source moves towards John, the distance between them, is it increasing or decreasing? Notice that the distance between the source and John is decreasing as the source moves towards John. And therefore, if the distance decreases, the wavelength will decrease because they both share the same unit, meters. Now, the distance between Sally and the source is increasing because the source is moving away from Sally. So because the distance between Sally and the source increases, the wavelength will increase. And you can see that the distance between wave crests are much higher than the distance between the wave crests on the right side. So as the wavelength goes up, the frequency goes down. So if the source moves towards an object, or if the object moves towards the source, the frequency will increase. If the source moves away from an object, or from the listener, or if the listener moves away from the source, the frequency will decrease. So anytime the distance between the source and the observer, if it's decreasing, the frequency will go up. If the distance between the source and observer is increasing, then the frequency will go down. So what equation can help us to quantify the frequency that the observer detects compared to the frequency that the source emits? The equation that you need is this one. FO is the frequency detected by the observer. Fs is the frequency emitted by the source. And it's going to be V plus or minus VO divided by V minus plus Vs. So V is the speed of sound, which is 343 meters per second at a temperature of 20 degrees Celsius. VO is the speed of the observer, and Vs is the speed of the source. Now the upper signs, colored in red, those signs apply if the source moves towards the observer or if the observer moves towards the source. The lower signs apply if they're moving apart. So if they move toward each other, the frequency will go up. Use the upper signs. If they move away, the frequency will go down. Now, me personally, I prefer to understand more and memorize less. And that technique usually works out. So let's say if you don't remember the signs, how can you tell if it's going to be positive or negative? Well, first you need to understand fractions. Whenever you increase the value of the numerator, the value of the entire fraction goes up. If you decrease the value of the numerator, the value of the fraction goes down. Now for the denominator, it's the opposite. If you increase the value of the denominator, or the bottom part of the fraction, the value of the entire fraction goes down. If you decrease the value of the denominator, the value of the entire fraction will go up. So let's perform a brief exercise. Let's talk about what signs to use for different situations. So let's say if the source moves towards the observer and the observer is stationary, the observer is not moving. If the observer is not moving, then V0 is 0. So that means that we don't have to worry about the signs on top. It's just going to be V on top. But the source is moving, so we do have a value for Vs. If the source moves towards the observer, should we use a minus sign or a plus sign on the bottom? Well, now let's think about it. We know that if the source moves towards the observer, the distance between the source and the observer is decreasing, which means that the wavelength is decreasing. And frequency is inversely related to the wavelength, so the frequency should go up. That means that the frequency of the observer should be less than the frequency emitted by the source. Should be more, not less. The frequency detected by the observer should be higher than the frequency emitted by the source, because we have an arrow going up. So since the frequency should be higher, should we increase the denominator or decrease it? Keep in mind, VO is 0, so we don't have to look at the numerator. We just got to focus on the denominator. As you mentioned before, whenever you increase the denominator of a fraction, the value of the fraction goes down. So we don't want that. We want the value of the fraction to go up because the frequency is increasing. So therefore, the value of the denominator must go down in order for the frequency to go up. So therefore, in order to decrease the value of the denominator, we have to use a negative sign. Because if we do V minus Vs, the value of the denominator will be less than V, and so the frequency will go up. And that's how you can tell which sign to use, by determining what effect this situation will have on the frequency, if it's going to increase or decrease, and then you could choose the appropriate sign. Let's try another example. So let's say if the source is moving away from the observer, what's going to happen? So once again, we don't need VO. The observer is at rest. So we need to focus on the denominator. So if the source moves away from the person, the distance between the source and a person increases, which means that the wavelength increases, and therefore the frequency will decrease. So the frequency detected by the observer should be less than the frequency emitted by the source. Now we're focused on the denominator. So if we want the frequency to decrease, we want the value of the whole fraction to go down, which means that we want the value of the denominator to go up. The value of the fraction and the denominator are inversely related. And if we want the denominator to increase, then we must choose the positive sign. So it's going to be V plus Vs. Now what if the observer moves towards the source and the source is stationary? If the source is stationary, Vs is 0, which means we don't need to worry about the signs in the denominator. We just need to focus on the numerator. So if the observer moves towards the source, what happens to the distance between the source and the observer? The distance is decreasing, which means the wavelength is decreasing, and therefore the frequency is increasing. So in order to increase the frequency, and therefore the value of the whole fraction, should we increase or decrease the numerator? The numerator and the value of the whole fraction are proportional. So if you increase the numerator, the value of the whole fraction will go up, and therefore the frequency detected by the observer will be higher than the frequency emitted by the source. And to increase the value of the numerator, we have to choose a positive sign. And so we'll use a plus instead of a minus. So as you can see, anytime the observer moves towards the source, or if the source moves towards the observer, use the upper signs. So hopefully this makes sense, and let's work on some problems at this point. The siren of an ambulance truck emits a frequency of 1500 Hz. What frequency will a stationary observer hear if the ambulance truck moves 30 meters per second toward the observer or away from the observer. So let's focus on part A. So we know that the frequency of the source is 1500 Hertz. And the observer is stationary. So VO is 0. The ambulance truck moves at a speed of 30 meters per second, so that's VS. And V is simply 343. So let's write the equation. The frequency detected by the observer is equal to the frequency of the source multiplied by V plus or minus VO divided by V minus plus VS. So VO is 0, which means we don't need to worry about the signs on top. The source is moving, so we need to find out if we're going to use a negative sign or a positive sign. So if the truck moves towards the observer, we know the distance is decreasing, which means the wavelength is decreasing, and therefore the frequency should increase. Now, we're focused on the denominator of the fraction, which is inversely related to the frequency. So in order for the value of the whole fraction to go up, the value of the denominator must go down. And that's going to cause an increase in frequency. So therefore, we want to use a negative sign and not a positive sign. So FO is equal to FS, which is 1500, times the speed of sound, which is 343, divided by 343, minus the speed of the ambulance truck, which is 30. (343) minus 30 is about 313. 343 divided by 313, that's 1.095846 times 1500 will give you a frequency of 1643.8. So as we can see, the frequency detected by the observer is higher than the frequency emitted by the ambulance truck. Now, what about part B? As the source moves away from the observer should detect a frequency that's less than 1500. So VO is still 0. We don't need to worry about the numerator. And we know the sign has to be different. If the source moves away from the observer, here's the source, here's the observer, and this time it's going this way. The distance between the source and the observer is increasing, which means the wavelength increases and the frequency should decrease. If the frequency decreases, the value of the whole fraction decreases, which means that the denominator should increase in order to decrease the value of the fraction. If we want to increase the denominator, we need to use the positive sign instead of the negative sign. So FO is going to equal FS times 343, that's V, divided by V plus the speed of the source. So this time it's 1500 times 343 divided by 373. 343 divided by 373 is about 0.91957 times 1500, and this should give you a frequency of 1379.4. A stationary loudspeaker emits a frequency of 1200 Hertz. So this is the frequency of the source. What frequency will an observer in a Jeep detect if the observer is moving at 25 meters per second So VO is 25. VS is 0 because the source is stationary. And for part A, the observer is moving towards the source. So let's say this is the source, and here is the observer. And he's moving this way. So if the observer moves towards the source, the distance is decreasing, which means the wavelength will decrease, and therefore the frequency detected by the observer should increase. It should be higher than the frequency of the source. So let's write the equation. So it's going to be V plus or minus VO divided by V minus plus VS. So we don't have to worry about VS. It's 0. We want the value of the frequency to increase. So we're dealing with the numerator. In order to increase the frequency, we must increase the numerator, which means that we must use the upper sign, the positive sign. So you can always use the upper signs if the distance between the source and the observer is decreasing. You can use the lower signs if the distance between the source and the observer is increasing. So this is going to be 1200 times 343 plus 25 divided by 343. 343 plus 25 is 368 divided by 343. That's 1.0729 times 1200. And this should give you an answer of 1287, rounded to the nearest whole number. Now for part B, the observer is moving away from the source. So that means that the frequency is going to go down, which means that we need to decrease the numerator. So we have to use the negative sign instead of the positive sign. So everything else is going to be the same, but it's just going to be 343 minus 25 instead of 343 plus 25. So 343 minus 25, that's 318, divided by 343, that's 0.9271 times 1200. So this is equal to 1112.5 hertz. So as you can see, the frequency is less than 1200 since the observer is moving away from the source. And when the observer is moving towards the source, the frequency increased to 1287. The siren of a police car emits a frequency of 1500 hertz. So that's Fs, the frequency emitted by the source. Now the police car is moving at 55 meters per second toward a speeding driver who is moving away from the police car at 50 meters per second. What is the frequency detected by the driver? So let's draw a picture. The police car is the source. It emits the sound. And the driver is the observer. Now the police car is moving towards the driver, and the driver is moving away from the police car. So this time, we need to use the numerator and the denominator in this problem. So let's write the equation first. FO is equal to Fs times V plus or minus VO divided by V minus plus Vs. So let's focus on the motion of the source. The source is moving towards the observer, which means that that motion alone will cause the distance between the source and the observer to decrease, which decreases the wavelength, causing the frequency to increase. And the source is associated with the denominator of the fraction. If we want the whole value of the fraction to increase, then the denominator must decrease, which means that we need to use the positive sign on the bottom, because the source, actually not the positive sign, that will increase the denominator. We want to use the negative sign in order to decrease the denominator. So anytime the source moves towards the observer, use the negative sign on the bottom. Now let's focus on the second motion, that is the motion of the observer. The observer is moving away from the source, which means that the observer's motion is such that it causes the distance to increase since he's moving away, and that will increase the wavelength, causing the frequency to decrease, which means that we need to decrease the entire value of the fraction. The observer is associated with the numerator of the fraction, and in order to decrease the value of the fraction, we must decrease the numerator, which means that we should use the negative sign. So now that we know which signs to use, we can now calculate the frequency. So it's going to be 1500 times the speed of sound, which is 343. And since the observer is moving away from the source, that's going to decrease the frequency. So we're going to put negative VO. The observer is moving at a speed of 50 meters per second. And the source, the police car, is trying to catch up to the driver. So the source is moving towards the observer, which means that should cause the frequency to increase. So we have to use a negative sign on the bottom. So it's 343 minus 55. Make sure you understand this, by the way. So you can always remember this too. If the source moves towards the observer, or the observer moves towards the source, use the upper sign, which we did in this example. The source moved towards the observer. If the observer moves away from the source, or if the source moves away from the observer, use lower signs. We did that for the observer because the observer is moving away from the source. So that can also help you too, if you prefer to view it that way. So Fs is 1500, and 343 minus 50 is 293, and 343 minus 55 is 288. Now 293 divided by 288 is 1.017 times 1500. So overall, the frequency increased slightly. And it makes sense why, because the denominator decreased more than the numerator. And when the denominator decreases, the frequency should increase. The siren of an ambulance truck emits a frequency of 1700. So Fs is 1700 Hertz. A stationary observer detects a frequency of 1825. Is the ambulance truck moving toward or away from the observer? Because the frequency detected by the observer is higher than the source, the frequency increased, which means that the truck has to be moving towards the observer. If the frequency goes up, that means that the wavelength decreased, which means the distance is decreasing. And the only way the distance could be decreasing is if the ambulance truck is moving towards the observer. So remember, if the frequency goes up, the source moves towards the observer. If the frequency goes down, the source is moving away from the observer. Now what about part B? How fast is the ambulance truck moving? So let's use the equation to calculate the speed. Now the observer is not moving. The observer is stationary. So VO is 0. So FO, that's going to be 1825. FS is 1700. V is 343. And we're looking for VS, the speed of the source, in this case the ambulance truck. Now because the frequency increased, that means that the value of the denominator must decrease in order to increase the value of the whole fraction. So we have to use the negative sign, the upper sign, instead of the lower sign. So it's going to be minus Vs. So let's divide both sides by 1700. 1825 divided by 1700 is about 1.07353. And that's equal to 343 divided by 343 minus Vs. So let's cross multiply. 1 times 343 is 343. 1.07353 times 343 is about 368.2208 minus 1.07353 Vs. So let's subtract both sides by 368.2208. 343 minus that number is negative 25.2208. And that's equal to this. So now let's divide both sides by this number. So negative 25.2208 divided by negative 1.07353 gives us the speed of the source, which is about 23.49 meters per second. A well emits a frequency of 420 Hertz in the ocean. So this is the frequency of the source. An observer in a submarine moving toward the well at 15 meters per second detects a frequency of 427.33. So that's the frequency of the observer, or detected by the observer. And the observer is moving at a speed of 15 meters per second. And the whale is approaching the submarine at a speed of 12 meters per second. Our goal is to find the speed of sound in seawater. So let's write the equation. FO is equal to Fs times V plus or minus VO divided by V minus plus Vs. So the source is the whale, and the observer is in the submarine. Now the source, aka the whale, moves towards the submarine. So that motion will increase the frequency. And the source is associated with the bottom of the fraction. So if the distance decreases, the wavelength decreases, the frequency should go up, which means the value of the fraction should go up. And to do that, we have to decrease the denominator. So we're going to use the negative sign. Now the whale, or rather the observer in the submarine, is approaching the whale. It's moving towards the whale. So if the observer moves towards the whale, the frequency should go up as well, which means the value of the fraction goes up, and the observer is associated with the numerator of the fraction, so we have to increase the numerator to increase the frequency. So we need to use the positive sign. So now that we know which signs to use, let's solve it. So let's plug in everything that we have into the equation. So FO is 427.33. Fs is 420. We're looking for V. That's the speed of sound in the medium, in this case in seawater. It's going to be V plus the speed of the submarine, which is moving at 12. No, the submarine's moving at 15. And then V minus the speed of the whale, which is moving at 12. So let's divide 427.33 by 420. So this is going to be 1.017452. And that's equal to V plus 15 divided by V minus 12. Now let's cross multiply. So 1 times V plus 15 is V plus 15. And this number times V minus 12 is going to be 1.017452 V minus 1.017452 times 12 is about 12.209424. This is 1V. Let's subtract V from both sides. And at the same time, let's add 12.209424 to both sides. So 15 plus this number is going to be 27.209424. And this number minus 1 is going to be 0.017452 times V. So now let's divide both sides by this number. 27.209424 divided by 0.017452 is equal to 1,559. So in this particular problem, this is the speed of sound in seawater. Jared hears a frequency of 1593 Hertz, and Rachel detects a frequency of 1417 from a moving ambulance truck. Is the truck moving towards Rachel or Jared? What would you say? Now, whenever the source moves towards the object, the frequency goes up. And if it moves away from an observer, the frequency goes down. Because Jared hears a higher frequency than Rachel, the source is moving towards Jared. So I'm going to put J for Jared. And Rachel must be behind the truck. The source is moving away from Rachel because she hears a lower frequency. She hears a frequency of 1417, while Jared hears a higher frequency of 1593. So the truck has to be approaching Jared. Now, what is the frequency emitted by the ambulance truck, and how fast is it moving? So we have two variables, the frequency and the speed. So we need two equations. So let's write an equation between the source and Jared first. FO is equal to FS times V plus or minus VO divided by V minus plus VS. So the speed of sound has to be 343 because they're not in the ocean and the sound is traveling through the air. The frequency that Jared hears is FO, that's 1593. We don't know the frequency emitted by the ambulance truck, so we need to find FS. We know V is 343. Jared is stationary. He's not moving. There was no speed given to Jared or no speed mentioned of Rachel. So we're going to assume that they're stationary. Now, we need to determine the sign in front of VS. Because the source is moving towards Jared, we know the frequency has to go up, which means the value of the denominator has to go down. So we need to use the upper sign. So it's minus VS. With this equation alone, we can't solve for two variables. Whenever you have two variables, you need two equations to solve it. So now let's move on to Rachel. Let's write an equation between Rachel and the source. So FO is going to be the frequency detected by Rachel. That's equal to Fs times V, which is 343. Now Rachel is stationary, so VO is 0. Now, because the source is moving away from Rachel, the frequency goes down, which means the value of the denominator must go up. So we need to use the positive sign instead of the negative sign. So it's going to be plus Vs. So now how can we solve for these two variables? What should we do? Let's isolate Fs in both equations. So how can we get Fs by itself? To do that, first let me make some space. We no longer need this anymore. Let's multiply both sides by the reciprocal of this fraction. So let's multiply by 343 plus Vs divided by 343. If we do that, these two will cancel, and those two will cancel on the right side of the equation. So on the right side, all we have is Fs. On the left side, it's 1417 times the numerator of this fraction, which is 343 plus Vs divided by the denominator of the fraction. So to move this to the other side, basically just flip the fraction. So now let's do the same thing for this equation. Fs is going to be 1593 times the denominator divided by the numerator. So I'm going to write it here. It's going to be 1593 times 343 minus Vs divided by 343. So once again, just multiply both sides of this equation by the reciprocal of this fraction. So that's 343 minus Vs divided by 343. So that these two will cancel and these two will cancel. And as you can see, on the left side is 1593 times 343 minus Vs, which we have here, divided by 343. Since both of these equations are equal to Fs, these two equations are equal to each other. So let's ignore Fs and set those two equal to each other. So let's get rid of this. Now, if we multiply both sides by 343, we could cancel the denominator. So 1417 times 343 plus Vs is equal to 1593 times 343 minus Vs. Now let's distribute. So 1417 times 343 is 486,031. And then we have plus 1417 Vs. That's equal to 1593 times 343, which is 546,399 minus 1593 Vs. So let's add 1593 Vs to both sides. And let's subtract 486,031 from both sides. $1417 plus 1593 is equal to 3,010 times Vs. 546,399 minus 486,31 is equal to 60,368. So to find Vs, let's divide both sides by 3,010. So 60,368 divided by 3,010 gives us Vs, which is about 20 meters per second. It's really 20.06, but we're going to round it to the nearest whole number. Now, Fs, the frequency of the source, we can use this side of the equation or this side. It really doesn't matter. But let's do it both ways so you can see it's the same answer. So Fs is equal to 1417 times 343 plus Vs, that's plus 20, divided by 343. So that's 363 divided by 343 times 1417, which gives us a frequency of 1500 Hertz. Now, if you use the other side of the equation, you should get the same thing. So Fs is equal to 1593 times 343 minus 20 divided by 343. So 343 minus 20 is 323 times 1593 divided by 343. And that too is 1500 Hertz. So we have the frequency of the source and how fast the ambulance truck is moving. So whenever you have two variables to solve for, you need to write two equations, and then you can solve it. A stationary source emits a 4500 Hertz sound wave directed at an object moving toward the source at 21 meters per second. So let's say this is the source, and we have an object. And the object is moving towards the source at 21 meters per second. What is the frequency of the reflected wave? So the source emits a sound wave. That sound wave will travel and be detected by the observer or the object, and is going to reflect back to the source. So let's focus on the sound wave traveling to the observer or to the object. Fs, the frequency emitted by the source, is 4500 Hertz. We need to find the frequency detected by the object, Fo. Now, because the object is moving towards the source, we know the frequency should go up. So using the equation, Fo equals Fs times V plus or minus Vo divided by V minus plus Vs. Vs is 0 because the source is stationary, so we don't need to focus on the denominator of the fraction. Now, if the frequency goes up, that means the value of the numerator must go up. So we need to use the positive sign. So we're looking for Fo. Fs is 4500. The speed of sound is 343 in air, and then plus the speed of the object, which is 21, divided by V. .343 plus 21 is 364 times 4500 divided by 343. You should get a frequency of about 4775.5 Hertz. So that is the frequency that is detected by the object. And that object is going to reflect that sound wave at the same frequency. So going backwards, we can now treat the object as if it's the source. And the source will be treated as the observer. So Fo now becomes Fs for the reflected wave. And we're looking for Fo, the frequency detected by the original source, which is now the observer in the second part. Some books will call it F double prime, and they will call this value F prime. This is the frequency detected by the observer, which is the frequency of the source for the second part of the problem. So now let's rewrite the equation. Fo is equal to Fs, V plus or minus Vo, divided by V minus plus Vs. So this is the new source, and we're looking for Fo. So it's going to be 4775.5 times v, which is 343. This time, the object is still moving towards the original source at 21 meters per second. But in this problem, we're going to treat this as if it's the source for the second part. So we're going to focus on the bottom portion of the equation. And since the source is moving towards the object, the frequency should go up, which means that the denominator should go down in value to increase the frequency. So we need to use a negative value to decrease the value of the denominator. So it's going to be 343. The observer, which is the original source, is stationary, so there's no VO, but VS is 21. So this new FO will give us the frequency of the reflected wave detected by the source. 343 minus 21 is 322. So 343 divided by 322 is 1.0652 times 4775.5. So the frequency of the reflected wave detected by the original stationary source is now 5087 Hertz. This is the last problem for this video. A stationary policeman uses his radar gun to direct a sound wave at 6,000 Hertz on a moving vehicle. The speed limit is 40 meters per second. The radar gun detects a reflected wave of 8,544 Hertz. Now here's the first question. Is the driver moving toward or away from the policeman? Because the frequency of the reflected wave is higher than the original wave, the driver has to be moving toward the policeman. Whenever the distance is decreasing, the wavelength decreases, the frequency goes up. If the radar gun detected a wave that was less than 6,000, then the driver would be moving away from the policeman. But now, the second part of the problem, is the driver speeding? Is he going faster than the speed limit, 40 meters per second? Well, let's find out. So there's two parts to this problem. The policeman is the source, and the driver is basically the observer, which I'm just going to put O for the observer. Now the policeman sends a sound wave at 6,000 Hertz. The observer detects the sound wave, and then the sound wave is going to bounce back from the observer, at which point the observer becomes the source, re-emitting the sound wave, and the policeman becomes the new observer, detecting the sound wave. In some textbooks, the original source frequency is known as F. The frequency that the observer detects is F prime. Now for the second part of the problem, the frequency that is reflected by the observer is now Fs, which is also still F prime. And the frequency detected by the policeman, which he's now the observer, is F double prime. So you might see those symbols in the textbook that you're using. So you can use them if you want to. I'm going to use them. Now the observer, we don't know how fast he's moving towards the policeman. The policeman is stationary, so Vs is 0. In the second part, Vs is VO, so VO is 0. And VO in the first part is Vs in the second part. So let's write our equation. FO equals Fs, or F prime equals F times V plus or minus VO divided by V minus plus Vs. So F prime is equal to the frequency of the source, which is 6,000, that's F, times V, the speed of sound in air, which is 343, Now the observer is moving towards the source, so the frequency should go up, which means we need the numerator to go up, so we're going to use positive VO. Vs is 0, so we don't have to worry about the bottom. So we just have V on the bottom. So this is our first equation. We have two variables. So we need to write another equation. So now let's focus on the reflected wave. So the new FO is F double prime, and that's equal to Fs, which is F prime, times 343. Now this VO now is the source, Vs. So we don't have a VO on top anymore for the second part. So it's 0. Plus or minus 0 is the same thing. Now, because the source is moving towards the observer, the frequency still has to go up because the distance between them is decreasing. And for the frequency to go up, the denominator has to decrease. So therefore, in order for the denominator to decrease, we need to use the negative sign associated with Vs. So it's going to be minus Vs. And F double prime is the frequency of the reflected wave, which is 8,544. So let's replace F double prime with that value. So now we have two equations and two variables. Keep in mind, Vs for the second problem is the same as VO. So we're going to replace this Vs with VO because they're the same thing. So now let's solve for the speed. In this equation, let's get f prime by itself. We can do that if we multiply both sides of the equation by the reciprocal of this fraction, which is 343 minus Vs divided by 343. So these two will cancel, and those two will cancel. So it's going to be this fraction times this number, 8,544, times 343 minus Vs divided by 343. Now this is equal to f prime. And f prime is also equal to this term. But let's get rid of Vs and let's replace it with VO, since they're the same. F prime is also equal to 6,000 times 343 plus VO divided by 343. So if we multiply both sides by 343, these will cancel. So since both of these equations are equal to f prime, we can set them equal to each other. So let's get rid of this. Now let's distribute 8544 times 343 is 2,930,592. And then we're going to have 8544 times VO, and that's equal to 6,000 times 343, which is 2,058,000 plus 6,000 VO. So let's add 8544 VO to both sides. And let's subtract 2,058,000 from both sides. So if we subtract these two numbers, you should get 872,592. And if we add these two, it's going to be 14,544 times VO. So let's divide both sides by 14,544. So you should get 59.997, which we could say it's about 60 meters per second. So that's how fast the driver is going. He's going way past the speed limit of 40 meters per second. So if he's not careful, he's about to get a ticket. So that is it for this video. Thanks for watching and have a great day.